Walk into any server room and you're greeted by a wall of blinking lights, tangled Ethernet cables, and dozens of identical gray boxes. But treating all these metal devices as if they do the exact same thing is the quickest way to break your network. Plugging cables into ports is the easy part. The real challenge is making sure the traffic flowing through those cables doesn't suddenly hit a massive bottleneck or leave your sensitive data exposed to anyone listening. You're immediately faced with a trade-off. Buy a simple device that lacks intelligence, and your network drowns in its own traffic. But spend your budget on a highly intelligent device for a basic connection, and you're paying for management headaches you don't need. When you choose the wrong hardware, you hit one of 4 distinct failure points: severe slowdowns from data congestion, security breaches from exposed internal traffic, total protocol incompatibility where devices simply can't talk to each other, or pure hardware overspending. To avoid those traps, we are going to map out the definitive network hardware hierarchy so you know exactly which box fits your specific bottleneck. Ultimately, network design is an economy of intelligence. You need to purchase exactly the level of traffic control your junction requires, no more and no less. Let's start at the foundational local layer. This diagram shows a hub, a purely physical layer device used to connect multiple computers together on the same local area network. The hub operates completely blind. When computer A sends a message to computer B, the hub doesn't know where B actually is. It just takes those raw data bits and aggressively broadcasts a copy out of every single port it has. As this slide details, copying those data packets to all interfaces forces every connected computer to process everyone else's traffic. It immediately congests the network and creates a glaring security risk. To solve that problem, you move one step up the hierarchy to the network switch. This schematic illustrates how a switch replaces mindless broadcasting with intelligent filtering and forwarding. It identifies exactly where computer D is and sends the data exclusively down that specific path. It pulls this off by operating at the data link layer. Instead of spraying raw bits everywhere, the switch organizes data into manageable frames and actively learns the physical MAC address of every single device plugged into it. This chart lines them up perfectly. The hub works in the physical layer, sending broadcast bits. The switch operates at the data link layer, sending targeted frames. Notice the bottom row. Storing MAC addresses is what prevents local traffic collisions. Because of this, hubs are essentially obsolete today. Switches require a slightly higher upfront investment, but they are absolutely mandatory if you want a functional, secure local network. But what happens when you need to run a cable further than the physical signal limit allows? This diagram shows a repeater. It is a strictly physical layer device deployed for one reason: to extend transmissions so a signal can clear an obstruction or cover a longer distance. It solves your physical reach problem cheaply, but it adds zero intelligence. A repeater blindly amplifies whatever it receives, meaning it will boost background static and interference right along with your data. Sometimes your problem isn't physical distance, but traffic volume. A single local area network can grow so large that it becomes overwhelmed by its own internal chatter. This graphic maps out a bridge. Operating at the data link layer, it sits between different network segments and decides whether to filter, forward, or block traffic from crossing over. By successfully isolating that traffic, a bridge drastically reduces overall network load. But there is a strict limitation. It only works if every segment it connects is following the exact same protocol. If you want to connect your private local network to the outside world, physical MAC addresses are no longer enough. You have to move up to the network layer. This illustration shows a router serving as the middleman between a home network and the broader internet. It handles data organized into distinct packets and routes them globally using IP addresses. Looking back at our comparison table, you can see the clear escalation in intelligence. A switch handles frames locally. A router handles packets globally. A switch relies on hardware MAC addresses, while a router navigates using logical IP addresses. However, a router still expects the data to speak the same basic language. It cannot connect entirely dissimilar network architectures. This diagram introduces the gateway. It acts as the ultimate translation device, capable of connecting two completely different environments together, like linking an old legacy mainframe directly to a modern IP network. That level of translation gives you incredible flexibility, but it comes at a steep price. Gateways are expensive, tedious to manage, and can easily become a catastrophic single point of failure. Connecting to the outside world also introduces the final variable, external threats. This graphic visualizes a firewall acting as the active barrier between your private network and the public internet. It explicitly blocks malicious traffic based on a rigid set of security rules. But a firewall isn't a box you just plug in and forget about. It requires constant, active rule configuration to ensure attackers stay out while legitimate business operations aren't accidentally blocked. Managing external connections demands the highest layer of device intelligence: IP routing, total protocol translation, and active filtering. That heavy processing requirement is exactly what justifies their higher costs and setup complexity. Let's put this together into a practical roadmap. The golden rule of network architecture is this: keep your internal network incredibly fast and simple, and push all the heavy intelligence to the outer edges. If you are a home user or building a basic lab, avoid hubs entirely. Rely on your ISP's modem-router combination for external access, and buy cheap, unmanaged switches if you just need extra physical ports. For IT admins and small businesses, a basic router won't cut it. You must invest in a dedicated hardware firewall at your boundary and use intelligent managed switches internally to segment your departmental traffic. If you're studying for an IT certification, memorize these strict pairings. Hubs broadcast bits. Switches filter frames using MAC addresses. Routers direct packets using IP addresses. And gateways translate between dissimilar networks. Remember, over-engineering your local connections burns your budget unnecessarily, but under-engineering your outer boundary is actively dangerous. Building a stable network isn't about buying the most expensive hardware on the shelf. It's about looking at your specific bottleneck and buying the exact box that has the intelligence to clear it.